The year 2038 problem relates to representing time in many digital systems as the number of seconds passed since January 1, 1970 and storing it as a signed 32-bit binary integer. Such implementations cannot encode times after 3 hours 14 minutes and 7 seconds UTC on January 19, 2038. Just like the Y2K problem, the year 2038 problem is caused by insufficient capacity of the chosen storage unit. The latest time that can be represented in Unix's signed 32-bit integer time format is 3 hours 14 minutes and 7 seconds on Tuesday, January 19, 2038. 231 to 1 equals 2,147,483,647 seconds after January 1, 1970. Times beyond that will wrap around and be stored internally as a negative number, which these systems will interpret as having occurred on December 13, 1901 rather than January 19, 2038. This is caused by integer overflow. The counter runs out of usable digit bits, flips the signed bit instead, and reports a maximally negative number, then continues to count up to 0, and then up through the positive integers again. Resulting erroneous calculations on such systems are likely to cause problems for users and other reliant parties. Programs that work with future dates will begin to run into problems sooner. For example, a program that works with dates 20 years in the future should have been fixed no later than January 19, 2018. In May 2006, reports surfaced of an early manifestation of the Y2038 problem in the AOL server software. The software was designed with a kludge to handle a database request that should never time out. Rather than specifically handling the special case, the initial design simply specified an arbitrary timeout date in the future. The default configuration for the server specified that the request should time out after 1 billion seconds. 1 billion seconds, approximately 32 years, after 1 hour 27 minutes and 28 seconds UTC on May 13, 2006 is beyond the 2038 cutoff date. Thus, after this time, the timeout calculation overflowed and returned a date that was actually in the past, causing the software to crash. When the problem was discovered, AOL server operators had to edit the configuration file and set the timeout to a lower value. Players of games or apps which are programmed to impose waiting periods are running into this problem when they attempt to work around the waiting period on devices which harbor the coding, by manually setting their devices to a date past January 19, 2038, but are unable to do so, since a 32-bit Unix time format is being used. Embedded systems that use dates for either computation or diagnostic logging are most likely to be affected by the 2038 bug. Many transportation systems from flight to automobiles use embedded systems extensively. In automotive systems, this may include anti-lock braking system, ABS, electronic stability control, ESC/ESP, traction control, TCS, and automatic four-wheel drive. Aircraft may use inertial guidance systems and GPS receivers. However, this does not imply that all these systems will suffer from the bug, since many such systems do not require access to dates. For those that do, those systems which only track the difference between times/dates and not absolute times/dates will, by the nature of the calculation, not experience a problem. This is the case for automotive diagnostics based on legislative standards such as CARB, California Air Resources Board. Another major use of embedded systems is in communications devices, including cell phones and internet appliances, routers, wireless access points, etc., which rely on storing an accurate time and date and are increasingly based on Unix-like operating systems. For example, the bug makes some devices running 32-bit Android crash and not restart when the time is changed to the date. Despite the modern 18 to 24-month generational update in computer systems technology, embedded systems are designed to last the lifetime of the machine in which they are a component. It is conceivable that some of these systems may still be in use in 2038. It may be impractical or, in some cases, impossible to upgrade the software running these systems, ultimately requiring replacement if 32-bit time_t limitations are to be corrected. MySQL databases built-in functions like Unix_timestamp will return 0 after 3 hours 14 minutes and 7 seconds UTC on January 19, 2038. Many data structures in use today have 32-bit time representations embedded into their structure. A full list of these data structures is virtually impossible to derive, but there are well-known data structures that have the Unix time problem. File systems. Many file systems use only 32 bits to represent times in nodes. Binary file formats. that use 32-bit time fields. Databases that have 32-bit time fields. Database query languages, like SQL, that have Unix_timestamp, like commands. Examples of systems using data structures that may contain 32-bit time representations include embedded factory, refinery control, and monitoring subsystems. Assorted medical devices. Assorted military devices. Any system making use of data structures containing 32-bit time representations will present risk. The degree of risk is dependent on the mode of failure. The Network Time Protocol, NTP, has a related overflow issue, which manifests itself in 2036, rather than 2038. The 64-bit timestamps used by NTP consist of a 32-bit part for seconds and a 32-bit part for fractional second, giving NTP a time scale that rolls over every 232 seconds, 136 years, and a theoretical resolution of 232 seconds, 233 picoseconds. NTP uses an epoch of January 1, 1900. The first rollover occurs in 2036, prior to the Unix year 2038 problem. Implementations should disambiguate NTP time using a knowledge of the approximate time from other sources. Since NTP only works with the differences between timestamps and never their absolute values, the wraparound is invisible in the calculations as long as the timestamps are within 68 years of each other. However, after a wraparound, the clients can still face two problems. They receive the date 1900-01-0100:00:00 UTC, not February 7, 2036, 6:28 and 15 seconds, plus or minus some leap seconds, as the new time. When a client tries to adopt this time and store it in Unix time format, as many embedded systems do, it will fail because Unix time starts at December 13, 1901, signed 32-bit integer, or January 1, 1970, unsigned 32-bit integer. This means that for NTP the rollover will be invisible for most running systems, since they will have the correct time to within a very small tolerance. However, systems that are starting up need to know the date within no more than 68 years. Given the large allowed error, it is not expected that this is too onerous a requirement. One suggested method is to set the clock to no earlier than the system build date or the release date of the current version of the NTP software. Many systems use a battery-powered hardware clock to avoid this problem. Even so, future versions of NTP may extend the time representation to 128 bits, 64 bits for the second and 64 bits for the fractional second. The current NTP4 format has support for error number and error offset, that when used properly should aid fixing date rollover issues. According to Mills, the 64-bit value for the fraction is enough to resolve the amount of time it takes a photon to pass an electron at the speed of light. The 64-bit second value is enough to provide unambiguous time representation until the universe goes dim. There is no universal solution for the year 2038 problem. Any change to the definition of the time_t data type would result in code compatibility problems in any application in which date and time representations are dependent on the nature of the signed 32-bit time_t integer. For example, changing time_t to an unsigned 32-bit integer, which would extend the range to 2106, specifically, in 6 hours 28 minutes and 15 seconds UTC on Sunday, February 7, 2106, would adversely affect programs that store, retrieve, or manipulate dates prior to 1970, as such dates are represented by negative numbers. Increasing the size of the time_t type to 64-bit in an existing system would cause incompatible changes to the layout of structures and the binary interface of functions. There is also no universal solution for the issue with DVB and ATSC real-time transmitted dates due to issues with legacy receivers. The issue has yet to be acknowledged or resolved by either organization. The only workaround would be to discontinue all time-related metadata services such as programming guides and automatic date synchronization after the affected dates. One possible option would be to create new table types for the affected part of the specifications and use ISO 8601 date strings rather than fixed integers as are used in ISO 9660 and ISO 13346 file systems. Most operating systems designed to run on 64-bit hardware already use signed 64-bit time_t integers. Using a signed 64-bit value introduces a new wraparound date that is over 20 times greater than the estimated age of the universe, approximately 292 billion years from now. At 15 hours 30 minutes and 8 seconds UTC on Sunday, December 4, 292,277,026,596. The ability to make computations on dates is limited by the fact that TM_year uses assigned 32-bit integer values starting at 1900 for the year. This limits the year to a maximum of 2,147,485,547, 2,147,483,647 plus 1900. FreeBSD uses 64-bit time_t for all 32-bit and 64-bit architectures except 32-bit i386. Starting with NetBSD version 6.0, released in October 2012, the NetBSD operating system uses a 64-bit time_t for both 32-bit and 64-bit architectures. Applications that were compiled for an older NetBSD release with 32-bit time_t are supported via a binary compatibility layer, but such older applications will still suffer from the year 2038 problem. OpenBSD since version 5.5, released in May 2014, also uses a 64-bit time_t for both 32-bit and 64-bit architectures. In contrast to NetBSD, there is no binary compatibility layer. Therefore, applications expecting a 32-bit time_t and applications using anything different from time_t to store time values may brave. Linux uses a 64-bit time_t for 64-bit architectures only. The pure 32-bit ABI is not changed due to backward compatibility. There is ongoing work, mostly for embedded Linux systems, to support 64-bit time_t on 32-bit architectures. 2. The X32 ABI for Linux, which defines an environment for programs with 32-bit addresses but running the processor in 64-bit mode, uses a 64-bit time_t. Since it was a new environment, there was no need for special compatibility precautions. Network file system version 4 has defined its time fields as struct nefs time 4 and 64_t seconds, u and 32_t n seconds, since December 2000. Values greater than 0 for the seconds field denote dates after the 0 hour. January 1, 1970. Values less than 0 for the seconds field denote dates before the 0 hour, January 1, 1970. In both cases, the n seconds, nanoseconds, field is to be added to the seconds field for the final time representation. Alternative proposals have been made, some of which are in use, such as storing either milliseconds or microseconds since an epoch, typically either January 1, 1970 or January 1, 2000. In assigned 64-bit integer, providing a minimum range of 300,000 years at microsecond resolution. Other proposals for new time representations provide different precisions, ranges, and sizes, almost always wider than 32 bits, as well as solving other related problems, such as the handling of leap seconds. In particular, TAI-64 is an implementation of the TEMPS Atomic International Standard, the current international real-time standard for defining a second and frame of reference. Deep Impact is believed to have been lost at the time its internal clock reached 232 1/10 seconds since 2000. On August 11, 2013, 38 minutes and 49 seconds UTC. Time formatting and storage bugs. Unix time. Year 10,000 problem. Year 2000 problem.